All right. Our next speaker this morning is Sylvia Wang, who joins us from Caltech. Sylvia's been working this summer with Ivanna and Anna, and she'll tell us about their project together, constraining M31's last significant merger using its system of tidal shells.
Oh, okay. Got it. All right. All right, yeah, thank you for the introduction. So why are we interested in studying Andromeda's last significant merger? Well, galaxy mergers in large galaxies such as M31 or the Milky Way play a significant role in the hierarchical assembly of galaxies, so understanding how they evolve over time and come to be the way they are. So there is some previous work done on this. So Tidal until 2013, this is a paper published also modeling M31's last significant merger. Basically, they had a composite potential model for the host galaxy, or M31, made up of a disk, bulge, and halo, and then a much more simple Plummer potential, which is just kind of like a density sphere for the satellite galaxy model. And they varied a couple parameters and then constrained these parameters to these observed data from the GSS, which is the giant stellar stream, one of Andromeda's tidal shells. And so I modeled my research with my mentor based off of this, also creating a composite potential for M31 and also Plummer potential for the satellite galaxy. And we varied the satellite mass, host mass, and also the time we ran the simulation for. However, instead of just using data from one of the tidal shells, the GSS, now data is available from Andromeda's other tidal shells, including the northeast shelf, southeast shelf, and west shelf. And the system of tidal debris we can use to constrain our model. And these all came from the SPLASH survey, which is the spectroscopic and photometric landscape of Andromeda's stellar halo. And basically, this makes available all the individual velocities and positions of individual stars in Andromeda's tidal shells. And this data comes from DEIMOS, which is on the Keck-2 telescope. And so I created my models using Gala, which is a Python package by Adrian Price-Wellen. And my initial parameters were derived from Tidal until 2013, which is the paper that I also modeled the rest of my research on. So my composite potential model M31 had also a disk, a bulge, and a halo. So the Miyamoto Nagai disk, Franco's bulge, and Navarro-Frank-White halo, these are all the models that were adopted by Tidal until 2013. So these are also the ones I used. And they're all relatively simple and also accurate for large galaxies like this. And then my initial parameters are also derived from several papers, including Tidal until 2013, Williams until 2017, and J. Canton. And so my Plummer potential model was also pretty similar. It's very much like a globular cluster. It's just a density law, basically, of a sphere. And using Gala, I was able to give it an initial position relative to the host galaxy, and also initial velocity relative to the host galaxy, and throw them at each other. And so the very first model generated this in terms of the stellar stream. So I've used a histogram in log form for the color. And so you can see there's kind of these stream-like features on the edge, but it's very difficult to see because you can only see it in 2 dimensions in X and Y here. And so I've decided to vary it a bit and see if I could see anything change. And so I changed the host mass a bit in this direction, increasing, and then also increased the satellite mass in this direction. And so you can see in all these different models, there's different features changing around the central part of the galaxy. So these may or may not be tidal shells, but qualitatively, we can just see from the histograms that we're making, you can see some semblance of tidal features around the central part of the galaxy. So in order to take a closer look at this, I converted them into phase space. So this is the original model I made in phase space, and this is in 3D, which is the radial velocity of the individual stars plotted against the 3D radius. And so you can see these like parabolas that are basically indicative of tidal shells, because essentially these stars are a large stream in orbit around the center of the galaxy. So you can see, the velocity is decreasing as the radius increases, and then it'll increase again as it loops back around towards the central part of the star. So this was pretty good news because my starting model was also already like pretty close to what I was looking for. There were already like tidal features that are showing up. And so now we had to make comparisons to observed data. This is, the figure on the left is from Escala until 2022, and this is just showing regionally where each of these tidal shells will lay. So this is the GSS that I mentioned earlier that Tidal used, and then these are the northeast shelf, and then the southeast shelf, and then the west shelf. And I've plotted the projected radius and then the heliocentric velocity of the individual stars collected through this splash survey on the right. So you don't see a parabola because this is like projected, it's like flattened, but you can see there's still like this kind of wedge shape, which still indicates that these stars are in orbit and they're forming shells. And I've also labeled the color for each of those individual tidal shells. So overlaying them with the phase-space plots for my models, this is a runtime of 3 gigayears. You can see there's definitely fewer parabolas in the lower mass models, which made me think initially these are probably not going to be the most accurate ones because we're looking for these tidal shells which only show up in the higher mass ones. However, I was a little unsure because the observed data doesn't even overlap. It doesn't even go out that far. It only extends to about 35 kiloparsecs. So I converted this to the projected radius. So this looks a little more similar. You see more wedge shapes. And surprisingly, the lower mass models actually do line up quite a bit. However, this is still only for 3 gigayears. I was still going to alter the time I ran the model for. So I decided to try just all the mass combinations in here, and then at 3 gigayears, 4 gigayears, and 5 gigayears. And so now I'm able to make quantitative comparisons using a likelihood function with all these different models. I have a total of 27. And then I use a likelihood function like this just for the velocity, and then the exact same one for the position. And then since it's in log, I can add them together. And what I would do is maximize this likelihood. So the most positive value for the model would be the most likely model, I guess, that would line up. And so that turned out to actually be a lower mass model. However, this one was run at 5 gigayears, which I did not have plotted out initially. So, I might have missed this one. But quantitatively, this would indicate that this is the most likely model that overlapped with observed data. And so this is a bit of a surprise, but it does actually look pretty close on the projected plot with the projected radius and the heliocentric velocity. So to conclude, we did find a model that had like a maximized likelihood, however, within just the parameters that we tried. So these 27 different models with 9 different mass combinations and 3 different runtimes at 5 gigayears with a satellite mass of 9.17 and a solar host mass of 11.8. And it's interesting because the lower mass models did generate fewer streams in 3D phase space. They generated more elongated stream-like features instead of like these tidal shells that we were looking for. So I think this we might be able to look into more in the future by changing the initial, possibly the phase space position and also the initial velocity of the satellite galaxy, which I didn't get a chance to touch this time, just because of the lack of time to run all these models, and also possibly other parameters. So increasing the range of the time we run the model for, and also maybe constraining a more specific mass for the satellite and host galaxy. Thank you.
Very nice. Questions for Sylvia?
Yeah, so I was kind of wondering where you sort of like draw the line in between a stellar stream and this kind of like shell. In like the plots that you created it with like the blue dots, are they more like shell-like or more stream-like?
Yeah, so this is a little difficult just to qualitatively, look at it and try to, draw a line, because some of these, they look a little more broken over here. It still has somewhat of a parabola shape. You see it's kind of starting to, get flung outwards. I didn't really have like a specific, line I would draw, because you see I did still include like the lower mass models in my quantitative comparisons. So I mostly use just looking at it like this in phase space to like get a general idea of what I think it might be. But I didn't use it to make any like hard conclusions or like to rule out any models specifically.
Other questions? So curious, maybe you might have said it and I missed it, but how long does it actually take to run these different models?
Yeah, so the models themselves, just for generating like these the data just for like each position and like velocity of each individual star, just about 5 minutes, maybe a little lower, a little higher, depending on how many gigayears I run it for. However, generating that likelihood value for each of those took longer. It took about 6 minutes just for like each individual model to get the likelihood value. One for the velocity and then doing it again for the position. Each of those took about 4 to 6 minutes.
Okay, great. Other questions?
So in this plot, I see that there is a trend line for low mass. Actually, yeah, low mass. That the things are flung out in a more defined path compared to the higher mass ones, whereas like flung out as in like scatter plots. So do you know any reason why that is happening?
Yeah, I don't know for sure, but I would think that because like these lower mass like galaxies basically when they interact, there's just not enough of it, I guess, like concentrated because it's like it's a density model, right? Just for the plumber potentials of the satellite galaxy. I think there's like it's just the mass isn't high enough for it to get like pulled into the galaxy and actually start orbiting, so it just gets flung outwards. Yeah, that's what I would think.
Let's thank Sylvia.